try to bring together like some things we've heard about yesterday about looking at tensor ranks, degenerations, restrictions, and so on, together with what we heard today, namely about tensor networks, how to optimize, how to use this ansatz class to talk about quantum many-body systems. So that's somehow the theme. I mean, we've heard a lot, so I'll just take my outline. So I'll start with an intro to tensor networks, but of course I'm in the very fortunate position that there had already been some intros today, so this will be short, mostly for making the connection and for setting notation a little bit. And then I talk about boundary states. So states in the boundary of this tensor network variety. And this will lead to a way to define an ansatz class that will include some of these states. And if there should be some time, I might also talk a little bit more about how to actually optimize in this class later on. But so let's start with tensor networks. Because I would like to have a little bit different point of view than the one that we've seen before. Okay, so I mean, we had a lot of motivation that this helps to describe quantum many-body systems, and that's of course also my motivation. And so what's the idea? So we look at the quantum many-body system, meaning we have a normalized pure state. We fix some local dimension, physical dimension, some spin, some qubit that we're interested in, and we're given a bunch of them, L, right? So this Hilbert space, of course, has a dimension which grows exponentially. So the dimension of the system Hilbert space, that will just be d to the L. And just this large number of free parameters somehow makes it difficult to even write down states of the system, letting alone optimizing over anything or computing a time evolution or something. But somehow you could say, right? I mean, the definition of Hilbert space somehow is the physical possible, right? So any state of my theory should be somehow in there. That's the idea of physical theory. But oftentimes you're more interested in the physically reasonable, right? Because typical states might look very different from what you have in experiment. And that there could be a difference between these two notions. You can see, so one measure for that would be the entanglement entropy. So let me just take this as one motivation. So what is that? So we define the entanglement entropy of some region as the trace over the reduced density matrix times log of the reduced density matrix of some subregion. So if we have our spins somehow arranged, say on a 2D lattice, and we can define some region A, and if the whole state system is in a pure state, we'll compute the reduced density matrix by just taking the partial trace over the complement of the region. And then we can ask, so how does a quantity behave? Depending on the size of A, okay? And if we take a random pure state in the Hilbert space, then typically this will scale with the volume of that region. Whereas, as we heard this morning, if, let's say, I mean, be very specific, 1D gapped Hamiltonian, we look at the ground state on that, then we have a scaling with the area of A, well, yeah, with the area of A, and in 1D this would be constant, right? So there's clearly a difference between these two, and I mean, oftentimes we are more interested in states of this form here. Now, then somehow to make this picture also, so what we'd like to do if we have this big Hilbert space of our full system, we'd somehow like to single out this physical corner. Which is not a subspace, just a set of states that we would be interested in. And on top of that, we'd like to find an efficient parameterization. For example, with a built-in area law like this. And that's in a way what tensor networks do. They have this built-in area law, and then one could hope that this might be a good ansatz class. And as we've seen, indeed, in many cases, this is also true. Okay, and so this then leads, for example, to matrix product states. And so what do I mean by that? So if we now write down a state in some product basis, so we have some coefficient depending on all the local basis states, and then I just write down I1 to IL here. So the system that I'm thinking of is just 1D chain of spins. And then saying that I want to look at the matrix product state has to do with the coefficient tensor. So I take all the coefficients, I put them into a single tensor. I want to IL, then here I have all the three indices, and then I assume that I can decompose this coefficient tensor where I put a limit, a cap, on these intermediate contraction dimensions. That's one way of thinking about matrix product states. And then, I mean, now we have all the ingredients, right? So I specify a local tensor, it has 3 legs, I do the contractions, and I can do this basically on any graph. Okay, so I'd like to add somehow a more, slightly more operational picture to this, which will allow us to make the connection to.
You're laughing about the straightness of this line.
Which will allow us to make the connection to degenerations and LUCC and slog operations, basically. And what's the idea in that context? So let's look at a single contraction like this, right? So what are we actually doing? I mean, this contraction here means that we take the sum over L A I J L B L I prime J prime, and this here are I prime J prime, and this is I J. So another way of saying this is that sum over L and L prime, and then put a delta function in here. I'm now back in. So looking at this picture, what this means when I do such a contraction here, what I actually mean is that in between I sum over these delta functions. And now I can just identify the cat here, the bar, with the dual space. Okay, so this is nothing else than a maximally entangled state, where sum L from 1 to D, and that's what we would call a maximally entangled state. So another way of looking at this whole procedure is that I have my 2 tensors, and then I apply this to my maximally entangled state up here, and that will implement this contraction at the end of the day. So coming back to our 1D system then, I can think about matrix product state as putting maximally entangled states along my 1D chain here. These would be the physical sites that I want to look at. And now in order to arrive at my coefficient tensor or at my state, I'll apply local maps, which map these d-dimensional spaces, these d-dimensional vectors down to the physical dimension. I do this everywhere. Okay. And this, of course, I can now do on any graph. So I can a graph with vertices and edges. And I put maximally entangled states along the edges. And then we apply local linear maps vertices. So how does it look like? So I get a state phi out as tensor product V in V, have a local map, and this is applied to tensor product over the edges of maximally entangled states of dimension D at the edge. And let's just call this over here omega G of bond dimension D. And of course, I mean, I could start to variate the bond dimensions everywhere, but I mean, for now, we just fix them uniform, and this will be good enough.
A's are what are the A's?
Sorry?
Linear maps, the A's are
The A's are linear maps, and indeed, what they will do, yeah, they will take the virtual indices. So we take CD to the power of the degree of our vertex, right? So all incidents in maximal entangled state, and this will go down to the physical dimension here. So if you think now about the PEPS case, all right? So let's do away with the wiggly things. Yeah, if I look at a local node, right, I would have in a regular 2D lattice, I would have 4 things coming in, right? So the degree is of course 4 everywhere, so I get 4 times C to the D, and then my local linear map would take this and then produce my local physical dimension D out of this. All right.
When you say maximal entangled state, you
Yes.
that definition of entanglement.
Exactly. So this is bipartite maximal entangled state, right? So I take the state with maximal Schmidt rank and where all the Schmidt coefficients are the same. So exactly where have I can also just write it down. So this omega D on some edge, this will just be the sum L from 1 capital D L non-normalized, because this indeed then implements the contraction, right? It's just so as I said here, what I'd like to do, right? Instead of thinking about these tensors that I contract, I want to think about that. This means that I have a state in the background to which I apply these local linear maps. And this is somehow a very operational way of thinking about this. I have an underlying state, some resource state, you could say. I'm allowed to do local operations, and this will produce the states that I'm able to see or prepare afterwards. So this is very close to SLOC or LOCC, right? But it's also, I mean, the other thing we can say here, right, is that actually tensor networks or matrix product states are just restrictions from this particular tensor that you pick. And that's somehow the point that I wanted to make. So if we talk about tensor networks, we are actually exactly in the setting where we want to think about restrictions from the tensor rank case, you could say. Are there any questions or comments?
Just to make sure if I
Yes.
I think I'm not understanding, but because we looked at the APR, you kind of look at them as one part goes to this one and one part goes to this one.
Exactly.
Okay.
Yeah, so the subtlety somehow is that these tensor products here are different, right? If you think about the MPS, they're shifted by half a lattice side, right? The maps are on side, the physical side, but the maximal entangled states go across physical sides. And this is of course still true. I mean, this is also true in PEPs, right? So these are the physical sides, and then indeed this one here goes across between 2 physical sides. Very good. I'll make some space. Yeah, maybe just let me say, so here we would say, right, phi admits a bond dimension D representation with respect to this graph. And maybe, so I'm not going to talk about this, but of course, I mean, in this language, it's also perfectly fine to somehow shift out the resource state. So one could, for example, think about tensor network representations based on GHZ states. And this would then indeed be tensor rank representations of these states, for example. Okay. Very good. Okay. So let's look at the boundary. And for that, just one more object that we want to look at. So as I said, right, so this is like for a particular state with the bond dimension D representation. So of course, now we can also look at the set of all tensor networks for graph D, where fixed bond dimension, physical dimension, and they're asked, I look at the set of all states that actually can be written in this way. Let me just make star here, right? And this will be one of the sets that we'd like to look at. And of course, I mean, I could, and that's also something we want to do, I could restrict this class further and require translation invariance, for example, which would mean that all the maps should be the same. And then, of course, I need a graph with a fixed degree everywhere. But I mean, I think it's clear what somehow the setting would be. Okay. And now we'd like to understand a little bit more about these sets. And there's a very nice lemma or result, originally from Landsberg, but there's a recent paper generalizing these results from Frieseke et al. And this is saying that if the graph has loops, so if G has loops.
Loops or cycles?
Sorry, cycles. Yes, very good point. Cycles. Then T and S G E is not closed. And let's say informal here, because there's some fine print on how D and D are related and so on. I'm not going to want to take that into account, right? But this is like, the later paper by Giesecke, they actually get in a more physical regime with the relation between small d and capital D. But generically, if you have cycles in your graph, then the set will not be closed. And so the question is, of course, are there interesting states in this boundary? And can we optimize over them in that case? And how do we parameterize them with the tensor network? Yes.
Is it closed? There was
Yes. Yeah, this is known. It's more a question if every cycle leads automatically to a non-closed set. But if there are no cycles, I mean, something like trees, lines, and so on, this is all closed.
Without asterisks. Like
Without asterisks, actually, in that case. Very good. So but then it makes somehow sense to look at the boundary. So this is our two boundary states. Right. So what we do now is we fix a graph. We fix a bond dimension. Well, and a physical dimension as well, of course. So this gives us the set. And then similarly as for the tensor rank, we can first of all define two functions. So we can, given some state that we could be interested in, we can look at the bond dimension of that state. That would be the minimum over all D, such that psi would actually be an element of this. And similarly, we can also look at something what we naturally can call the border bond dimension of a state. And then you ask just if psi is in the closure like this. And now, of course, I mean, it's clear that we have this inequality exactly in the same way as in bond and border bond. Rank and thank you, rank and border rank case. But the question is, can there be a separation, and how large can the separation be? That is also true, but of course, that's what I mean. And maybe just let me say also why would we be even interested in a question like this? So why do we want to bring down the bond dimension? Because if you think about optimization or efficient representation, then of course the bond dimension tells us how many parameters do we have to fix in order to specify the state. So the smaller we can choose the bond dimension, the smaller is the complexity of the problem that we end up with. Or I mean, we could also turn it around and say that somehow the minimal bond dimension for a state will tell us something about the complexity of that particular state that we are looking at.
So can you write so if you want to obtain the rank, I mean, for all the tensors that have a rank smaller than R, what would be the corresponding graph here? Or is it possible even to obtain it in this?
You want the tensor rank, or?
Yeah, let's say the tensor.
No, but then basically I would switch out this thing here and put the GHZ state, right? Because that would be the unit tensor, and then you just put the GHZ state here.
There's no graph.
It's more like a hypergraph.
Yeah.
No, indeed. Then you go for so all this here, right? You can play the whole game also with hypergraphs, and then you would put, for example, GHZ state on the hyper edges, and then of course, if you take like the hyper edge that contains all vertices, then you exactly get tensor rank. Yes. Yeah, good point. Exactly. Okay. Oops. So let's look at this boundary a little bit more. And
So both the border bonds, they can be far apart. Can they be far apart?
I'll give some examples. It's the same as for rank and tensor rank. We have some examples, right?
Yeah.
About border rank and tensor rank. I'll give some examples. In general, of course, we don't know.
No, but there we have some gaps.
Yeah, I'll provide some examples with gaps, actually system size dependent gaps. So we can get a system size dependent separation. But the problem will be that I'll cheat a little bit because I can only show that in the translation invariant setting, because otherwise it's hard to get lower bounds. Right? But we come to that in a second. Let me just say, so how can we even get these states at the boundary? And that's of course the idea of a degeneration, right? So I somehow have my set of bond dimension D states, and then down here I have my boundary. So if I have a state that lives there, I have a sequence of states in the set that will converge to that. But as for degenerations and tensor rank, it turns out that these can be chosen as rational curves again. Okay, what do I mean by that? So take some phi in the boundary, and so I have a sequence of phi-n's that will converge to phi. But it turns out that I can directly write down local linear maps that will implement this in the following sense. So they exist, local linear maps. They depend on a parameter epsilon, but they do so polynomially. So I can expand I from 0 to eta. And then I have some, well, let's call this R, so it's consistent with what I've written here. Otherwise, there will be chaos. in this sense. Yeah, and I can write down phi epsilon. This will be just the tensor product again of these states. V in the vertex set. I apply this to omega g d. And then if I expand, so oops, this of course still depends on epsilon. Now I apply this everywhere and then I make an expansion. Okay. And the promise is that I can find these in such a way that in the lowest order, I find the state in the boundary. But then on top of that, there will be some additional states. Epsilon a plus I, and then there are some phi I twiddles here. So that's always possible. But of course, I will have a certain approximation degree here. So this A here we call the approximation degree, and this will be what we call the error degree. So the order of that polynomial, and that's what we would call a degeneration. And that's completely analogous, completely the same as in the tensor rank business, except that we have somehow now a different state that we put underneath everything, different entanglement structure. Okay, and then we can of course see if we take epsilon minus a psi of epsilon, then this will converge phi, I should say. This will converge to phi if we send epsilon to 0. But some of the important point to note is that we cannot take the limit without applying it to the state. If I just would divide this by epsilon to a and take the limit, I will not find in general local linear maps that do this transition, because then it would actually be a degeneration. So it's a kind of a global limit that I find here. Very good. So now we come to examples of these separations. If there are no additional questions.
Remark, I didn't quite understand what.
Yeah, I mean, so the point that I want to make, right, is that indeed you can recover the state, because I mean by definition we go to the boundary, right? So in the limit, in the closure, we'll end up there. But this does not mean that we can directly find limiting local maps that will do the same transformation, right? Because otherwise we could somehow stop and forget about the whole thing, right? Because then I say, okay, but then I mean the whole thing is closed, right? Because there are these local linear maps, so there's nothing to do. But the point is that this limit might not exist individually as local maps. Only if I apply it to this particular resource state do I get to a limit. That's somehow the point here. Okay, very good. So what kind of separations do we know? So here's one. We can take the GHZ states on 3 parties. So this will be 0, 0, 0 plus 1, 1, 1. And this has border bond dimension 2, and we can show that the bond dimension of the same state is actually 3. So we have at least one example with an actual separation. I mean, this might not sound so impressive, of course, but now you could roll this out on a lattice, of course. And that's something we also have looked at. I don't want to talk about this too much, but of course, if you have this on every plaquette, this will accumulate. So you actually save system size dependent again. But we also have other examples, and I mean the most well-known example, I guess, is the W state, where you somehow have a similar thing also in the tensor rank business. But there we have to go to the translation invariant setting.
That's probably
Sorry. Yes.
probably is true about it. This would understand. So on your example on the GSM, so is this the fact that the
It's not directly Strassen.
I'm thinking that the GSZ as it is rank 2 as a tensor rank, but in the limit, if you write sequence with it, then you get to a rank 3 tensor. It's that's the W state, right? In the limit of let me say it in another way. So in the closure of the rank 2 tensors, there are rank 3 tensors.
Oh, that's true. But the GZ state is tensor rank 2, right?
Yeah.
It might be that would be a way to prove it.
Tests are not closed.
Yeah, exactly. That might be a way to prove it. We show that it's just impossible to satisfy the equations explicitly, but it's a good point. Probably that would be a way to do it.
No, if this is the case, then this can give a hint on where
to look for others. Yeah, that's a good point. I don't know actually, but it's a very good idea. Okay, so one example, right? So we are in the translation invariant setting, and we look at the circle. So MPS with periodic boundary conditions, you could say, like this, and there. If we take the W state, so the state 1, 0, 0, all the way plus permutations, you put the 1 everywhere. This will have also border bond dimension 2. Oops. So on L lattice size. So border bond dimension is independent of system size. But if we look, so maybe I should write translation invariant here. But if we look at the translation invariant bond dimension of that state, we get a lower bound, which is of the order of L to the 1/3 over log L, and that so this lower bound uses the quantum Wieland inequality, and it's actually due to David Perez-Garcia, some old result. But so there we actually have a lower bound. And somehow the funny thing is the best construction is linear in L, because what do? You take the open boundary conditions, you just do SVD everywhere, right?
What is linear? Sorry, what is linear? The best construction?
The best construction for translation is, so what does it mean, right? So we should find a single tensor A, right? Maybe it depends on L, right? On the actual length. But then if we string it up L times the same tensor, close this, then this should be the W state on length. That's the thing we have to find. Yes. Okay.
The bond dimension bigger than.
Yes, and here the bond dimension has to grow at least as L to the 1/3 over log L.
Should write omega.
That's also what I wanted to do, actually. Thank you. It's also getting late. Very good. All right. But somehow the best way we know in many cases to produce this kind of translation invariant things is we start from the open chain. We do it from left to right. Write down a normal MPS, and then we twirl that thing. So we take the local tensor and we shift them one after the other, right? And then we sum up all these states. Makes sense. So I start from this thing, right? Now I shift, so I get the state looks like this, and then I do also the next shift. They all produce the same state, so I can just sum them up. But I get the same state by just taking the direct sum of the local tensors, and these are now translation invariant.
That's why you get an OL.
This is how to get the linear case. basically.
So that's, but that, you mean that's the upper bound on the bond?
No, that's the best construction that we know to get an actual representation, because so this is a lower bound,
Yeah.
right, that we get. But if you ask me to actually write down a translation invariant representation of the W state, then the best I can do is with the linear.
That's an upper bound, right? So that's an upper bound on bond TI.
No, this is a lower
That's an upper
bound.
bound, but what we just mentioned will be is
Exactly. That's the best upper bound that we know for now.
But
Exactly.
that what's the exactly L or O?
2 times L.
2 times.
2 times L, because each of those has dimension 2. So and the point is that they are already all the same except for one tensor.
What was the lower bound? L to the?
L to the 1/3 of
to
a
the
log
one.
L. So that would be an interesting question, whether one could actually get something sublinear as a representation, or find any somehow translation invariant state, right? That, I mean, of course, it's not constant, but would be sublinear in the end for a translation invariant state. I at least don't know any example of this. Very good. And then, since we're going to use this in order to define our ansatz class, we can generalize this a little bit to weight states. Let me write them down. Of course, we're going to use them a number of times. And I'll call them pi. And they have parameters a, eta, and length. And this will be sum over I1 plus all the y up to IL equal to A. This fixes the local dimension, IL smaller than eta. And then we just sum over the corresponding basis states. And for A equal 1, this would be the W state. And there basically we get the same bounds. So somehow we can use the same construction to get this kind of A to the 1/3 over log L behavior as a lower bound for the bond dimension. And the border bond dimension will just scale linearly with A, but will be independent of system size. I can write it down, but I think that's basically the same behavior.
These are side tensors, but you're not using that. Are you using that?
We're using that in the proof.
But you're not using complexité or not?
Sorry?
Are you using?
No.
No.
I mean, we're not taking tensor powers, right?
No, right.
So this is really like not in the asymptotic regime. That's another interesting question. Somehow, what would be the asymptotic bond dimension that one actually needs, and that I would find very interesting, whether one could connect that to topological order or something. But that will be one of the open questions somehow.
Right, so asymptotically, the bond dimension might go down. So.
Yeah, that's a good question, right? It might. But it's a bit tricky.
Oh, you don't know. You cannot translate these border bond bounds into asymptotic bounds.
Not quite clear, I think. I mean, we talked a little bit that you basically get the same monotones, I guess. I mean, because direct sums are of course fine. If I take direct sums of local tensors, that's perfectly fine. It will give me superpositions of states. I just increase the number of superpositions that I have in my expansion somehow. So one could actually use these kind of simmering constructions also here.
No, what I meant with bordering, if you have a bordering bound, you also have asymptotic rank bounds. You can.
Oh yeah, but this will also be true, because of course, I mean, I can supply a GZ state. This we'll see that in a second when I talk about the ansatz class, because of course we can now transform the degeneration into restriction again.
So yeah, exactly. So asymptotic bond is at most border bond.
Oh yeah, that's true.
Is it most bond? So you already have that.
Yeah, this is of course, that of course is true. Okay, let me. Very good. Make some space again.
This is, it's a generalization of W, right? That they are allowed to be 0. right?
Sorry.
Yeah, oh yeah, you're allowed it to be 0 to X. You want W also to be case.
Yeah, it's just, I mean, it's a question of counting there, no?
Yeah.
The local dimension. That's the
Weak inequality.
oh, yeah. Sorry. Yeah. Indeed.
There's still a way.
Exactly. That's
I'm getting rid of it.
to catch the audience, right?
And how do you choose the number of sides of the graph?
In which case?
Well, without it says.
No, this is just the circle, right? And then the number of sides corresponds to this expansion. This would be side 1, side 2, side 3, and so on. So L is system size again, and same up there. Yes.
These weight states, they span the symmetric span.
Yes.
Does it give you any upper bound on the maximum bond dimension?
Yeah, I mean, we know the maximum bond dimension, at least the bound. And actually, we're going to use this. So they have small border bond, they have small border rank. That's what we're going to use. Or we're going to use that they have also small bond dimension. Because, yeah, I'll talk about that in a second. But it's a good observation. And let me maybe just generally also mention that what we also know is that if we look at the circle and the closure, then the largest separation we can ever get in the general case, so without translation invariant, this will be quadratic. And this is due to the fact that if I start from the closed chain and I now cut this open, I know this thing is closed. So there will be nothing in the boundary. So how can I restore somehow this thing? I can just put a second line of maximally entangled states up here, and then do entanglement swapping from this side to this side to restore the missing link. Okay, so that's why we get a d squared at this side. So this is what we know in the general case, but yeah, I mean, I've seen the examples that we have for now. And we can also get a bound for general graphs. We don't know how tight this is. But there, oops, so this is a general graph. And then we get d to the number of edges minus the number of vertices plus 2. And this is basically putting an additional, you put an additional resource state to turn a degeneration into a restriction. And then the question is, how can you put this through your graph? Because this will then, of course, increase your bond dimension. And somehow this is like the construction that we have at the moment. Very good. So in the last minutes, let me just write down what actually our ansatz class is. So, I mean, maybe just one final remark. So these were more or less very abstract states, right? You could wonder whether they have something to do with physics. But what we can actually also do is we can write down explicit examples of like spin systems where those kind of states in the boundary are the unique ground state of a local Hamiltonian, like nearest neighbor Hamiltonian. So we can build a parent that will have exactly such kind of state as a ground state, but they still lie in the boundary of some small bond dimension. And then it turns out that if you try to do numerics, you actually need quite a large bond dimension to represent, I mean, to find the state again, as compared to our ansatz class. So what's the whole idea? And I mean, this goes back to a paper by Jeroen and Matthias, about how to turn degenerations into restrictions. So let me because I of course erased it a second ago. So let me just write down what we have. Right. Phi plus epsilon A plus E. And then we have our additional states here. So one observation, if we divide the whole affair by epsilon to the A, yeah, then we see that on the right-hand side we have a polynomial of order E. So one direct way to somehow get this state phi out is to think about this whole thing as a polynomial and then evaluate this at E+1 points, epsilon. And in that case, we can just extrapolate to 0. All right. So that's a way of getting the exact state out without having to evaluate this thing at epsilon equals 0. Now we just follow this rational curve. We know it's as long as we know the degree, and then we can just extrapolate. And this kind of extrapolation can actually be done by also putting in an additional state. And in fact, it can be done by using these weight states. So one can show that if we have a degeneration of this form, then there exists maps BV, which now go from, well, the local virtual space that we have anyway. So this is the degree of our vertex V, tensor C to the eta plus 1. So this maps again to physical dimension, such that phi can be written as tensor product BV, BV. And now we apply this to our maximally entangled states given by the graph. Tensor the weight state A, eta, and L. So there's one condition that we need, namely that eta is larger than E in that case, just to make it a bit more compact here. Okay. So now we recover the correct state again. And that's nice, because now we have a way to actually parameterizing states in the boundary as a normal tensor network. By, instead of using EPR pairs, we use these additional weight states. So the kind of set that we want to look at will be exactly those. So this will be our boundary tensor network states for graph with one dimension D, physical dimension D, and then we have the A and eta parameter also. Right.
This is always in the boundary.
No, that's a very good remark. That's what I want to say. No, it's not. Right. So the point is that if we wanted to make sure that we only optimize over the boundary, we would have to make sure that we only use B's, which somehow kill the low orders. This somehow would be a polynomial equation that we would have to check and satisfy. This would grow with system size. So instead, what we're saying is, I mean, we're interested in good approximations to the physical states anyways, right? So let's just make a relaxation where we go over a set that contains the states that we're interested in, but might contain something more. Right?
This covers the boundary if you have enough.
It does not cover the full boundary. It only so looking at, so you should somehow think about the approximation degree and your error degree as an additional refinement parameter, right? So now you have somehow one dimension and the error degree as additional refinement parameters that you can of course turn on, increase, right? But this will then lead to a more complex to a more complex weight state that you have to put, which then has a larger bond or larger border rank, which will like turn up in all computations that you have to do on that.
But E is always bounded, right? You know what you know how big to put E. because
Exactly, but this is why I said eta here, right?
no, but then you also know how big to put eta, right? Because you know the size of your tensor, then you know. Then you
This might depend on
that
system.
depends on A still.
Yeah, and then it can also grow with system size,
Yeah,
right? It can grow with system size, so that's why we put a cap, right? It's true. I mean, in the general case, I can of course like make it bigger and bigger.
So the system size is L.
The system size is L, but somehow we look at cases where we put a cap on these.
So you need capital D, small d, A, and eta.
Somehow eta, you know how big to put eta, I think. But depending on A, capital D, and small d, no?
If I wanted to cover everything, I mean, I also know how big to make D, right, to get all states, but it might be exponential in system. Typically, it's exponential in system size. So I mean, it's true, right? We know how large we would have to choose them in principle to get all states in the boundary, but somehow I think conceptually one should think the other way around, right? You have your computational resources, so you put a cap, and then these are the states that you actually cover. In this.
Plus one tensor L. Right?
Sorry?
Beta V or BV is now. The second tensor factor should we see a plus one tensor L.
Sorry, what? I think I have to go. Which ones?
BV is a non-CD tensor degree of V. One of them.
Here?
Yeah. The second tensor factor.
This one?
Should that be tensor L times?
No, this is a point that we put a local cap. Right. So indeed, if I want to go for like arbitrary, I mean, I wanted to write any state in the boundary, then this might have to grow. This might have to grow with L, I think.
The X chi lives in that space tensor L times.
Yeah.
The whole
See, the local dimension is kept by eta, right? So the local basis vectors, each of those, they run from 0 to eta. So that put eta plus 1. Yes, I did put eta plus 1. Right, just because it runs from 0 on. So locally, the local dimension is still fixed. Not of chi.
So now the parenthesis on.
Isn't it the product of the vertices?
So
Every vertex has CD to the
Yes.
tensor.
So this is a single local map, right? There are all the maximal entangled state coming into that vertex, right? Then I add this global state chi, which itself has a local dimension, which is eta plus 1. And so I also act on that degree of freedom. I mean, think about if you would add a GXZ state, right? Then you would also locally add finite dimension, even though you put 1 everywhere. Same as in the normal degeneration case. Very good. Now, we don't have much time left. Let me maybe just make a few remarks, right? So it turns out that we can actually efficiently optimize over this class, basically with the existing algorithms, with very small changes, and it's all based on the question how to compute expectation values.
Optimize means what do you optimize?
So for example, you want to minimize an energy, right? That's what I wanted to say actually. So if we have a degeneration, right, then the important question is, if we have this, can we efficiently compute expectation values with respect to the actual state in the boundary that we would be interested in, right? Because this will then allow us to do a gradient descent or something for finding an energy, right? So what you actually might want to minimize would be the expectation value of your Hamiltonian divided by the norm of your state. That would be like typical function that you want to minimize in order to find the ground state, right? But for that, you have to be able to compute these expectation values. I mean, then of course you take the derivative, and this will be a linear function of one of the local tensors and so on. It's not make it too complicated. The question is, can we do this here efficiently, and does it actually help this whole procedure to do this more efficiently than doing this in the boundary directly, right? So there are two questions. First question is, I mean, the state is at the boundary. So by definition, right, I can find a good approximation of that state in the boundary already from my original set, right? So why on earth would I ever be interested in doing this whole procedure if I want to do this numerically? But this has to do with numerical instabilities, right? So, I mean, we can already see this here, basically. So now I divide by this epsilon out, there will be very small numbers which somehow have to go away, right? So this becomes very ill-conditioned, and it becomes even more ill-conditioned if we think about what we actually want to do. So let's say I have the state from the degeneration to normalize it. So here I would put in a small epsilon to actually approximate my state in the boundary. And then typically, so if I want to estimate an energy with respect to a local Hamiltonian, this approximation has to go down with system size, because I have to estimate basically an extensive number of local expectation values if my Hamiltonian is a sum. So, right, my H is usually given as a sum of local terms. So this kind of approximation has to be the order delta L to the alpha, depending on the dimension of my state. And this will translate then, I mean, if I put this back to the epsilon, this will mean that these quantities will also be of the order of this. So I have to make calculations which are precise in each entry in the order of a small number, and this leads to instabilities at the end. Whereas if I just can put in a finite epsilon in this kind of expression, I'm fine, right? And then I can extrapolate. And that is also the idea, and this will be like the final point that I want to make. So observe, right? I said this was a polynomial, so we can extrapolate. So this is, of course, also a polynomial in epsilon. And so if we now, in this ansatz class, find a degeneration for this state, we can play the whole game again. So we get a degeneration for this state. So this will again be a polynomial in some epsilon. So we can do extrapolation if we know the degree of this polynomial. And so we can get expectation values by just evaluating this for fixed epsilon at sufficiently many points and then extrapolating. And this is somehow what we can do at the background. But the point is that here we have to contract a tensor network with a smaller bond dimension, right? As compared, so we basically have a choice. We can make a contraction on the tensor network with a large bond dimension, right? Which is very expensive if it's like a 2D model, right? I mean, either it's very expensive or we have to cut a lot of information away, right? Whereas here, you just can like linearly number of many times contract a tensor network with a smaller bond dimension, and this turns actually out to be more efficient. And in some way also more stable, because we don't have to make as many approximations along the way if we have to cut down in order to keep the whole thing manageable. Okay, that's actually everything I want to say. So I hope I have you convinced that there's an interesting connection between degenerations and restrictions to tensor networks, actually, that all these concepts also pop up in this area, and that there are some interesting questions that one can play with. And then finally, so there is this ansatz class that we somehow find, and it seems to work quite well for certain spin models. I mean, I didn't show you any numerics, but I thought on this conference it's maybe more interesting to look at actually conceptual questions. Thank you very much.
Thanks.
More questions?
Yeah, maybe first thing is why do you want there to grow like 1/n?
You mean the one up there?
Yeah.
Because I mean, if I estimate an energy, right, then I have local expectation value, a number of local expectation values that grow the system size, right?
The norm of H grow.
Exactly.
And you want that.
I mean, generically, that's what happens, right?
Okay, and so that's the other thing is okay. So yes, you reduce one dimension, but you add this extra system, right? So your now the way you represent your state is also a little bit larger because you increase.
Exactly.
So how do you quantify the gain?
Yes. So we know. But now somehow there are two ways to deal with this, right? And that is what I wanted to say here at the end. So one way, right, is if I now also take the border rank representation of that thing, right, which will scale it as A+1. So the border rank of that thing is system size independent. So it scales as weight +1. Then I don't see any additional bond dimension because I'll evaluate this expectation value for fixed epsilon with the original bond dimension because I just use the degeneration from before. And then of course I have to do it A+1 square times, basically, times system size. But somehow I have a smaller contraction that I have to do, and then linearly many times. The other thing is I could write this as an MPS. This has bond dimension A+1. So then my actual bond dimension, and I mean, it's a very good question. So the new bond dimension would scale as D times A+1. But so from the numerics that we see, we see that actually minimizing in this class over these B's with this additional weight state seems to be much more stable than to go to larger bond dimension. So if I just count at the end number of parameters in my tensor network before I somehow get to the same precision in some optimization of the energy, for example, then it seems that this is much more stable and also much faster and needs less parameters. I mean, as long as there is a difference between border bond dimension to begin with, of course.
Yeah, is the closure of TNS always seriously closed? So you can,
Sorry?
is the closure of the TNS set always seriously closed? So you can find polynomial equations.
I think so. Yes, it's a variety. The closure is an algebraic variety. Yes, indeed.
So that's useful to kind of have everything.
Yeah, that's a good question. I guess that could be a program that one could try. That's true.
You cannot separate it from. You can use equations to check the border, but not separate from.
You mean you don't know whether it is as a bond dimension representation in the first place? Yeah, that's true.
All right. Yeah. Okay. Thanks again.